There is a fundamental order from the atomic level all the way to the far reaches of the Milky Way galaxy. We know the patterns for the atoms in far off stars, and we know the patterns for the atomic structure, and they're all unified. There's a fundamental order, and it's based on the six-dimensional geometry of our tetrahedral coordinate system. Well, what we're doing is we're challenging the uncertainty principle of Heisenberg and the Richard Feynman theory of cloud theory. We're saying that there is order, there is geometric order for the positions of the electrons and the nucleons of the atom.
Currently, it is believed that we cannot determine where the atomic particles are. Our triangular system provides a means to locate the atomic particles with considerable certainty. This provides an opportunity for the world to generate solutions to many current problems. As we discuss different aspects of the atom, we will be including applications of our theory. A triangular plane is comprised of three vectors, where each vector is at 60 degrees to each other. So this generates an equilateral triangle where each side of the equilateral triangle is a dimension, so 3 dimensions on a flat surface. Crystallography recognizes these as Kagame lattices. This model of the cube octahedron is composed of 4 triangular planes. 1, 2, 3, 4. And each of these triangular planes has the overall shape of a hexagon. Where these 4 hexagons intersect generates the 6 axes of symmetry of the cube octahedron, which are the 6 dimensions. We have labeled them RSTUVW as the 6 letters that precede XYZ. They are color-coded, 4 sets of parallel edges for each dimension. So the R's are in red here and here. The S is in sulfur here and here. T is in tangerine here and here. U is in ultramarine blue here and here. V is in violet over here, and the W is in white over here. At rest mass, the electrons spin like gyroscopes following polyhedral geometry, primarily based on 3 axes of symmetry, 4 axes of symmetry, and 6 axes of symmetry. This is also seen in crystallography. The electrons are located at either a polyhedral vertex or at the center of a polyhedral face. The electrons spin in pairs, and this could connect to action at a distance. We believe that the wave-particle duality is in reality the profile of a spinning electron, and if viewed with depth information would reveal a corkscrew motion. The line between the pairs of electrons is a polyhedral axis of symmetry with the nucleus at the center. This is confusing, so try this at home. When you demonstrate the spinning pairs of electrons where both electrons in the pair are spinning in the same direction, it is hard to tell if they are spinning clockwise or counterclockwise. So try this at home. When you observe your left hand from the outside, the electron appears to be spinning counterclockwise. And when you keep the same motion and you observe your right hand from the outside, the electron appears to be moving clockwise. So to simplify this confusion, we say half of the pairs spin in one direction and half of the pairs spin in the opposite direction, and this is what keeps the atom in balance and holds the electrons in place at rest mass. Also in balance is the electromagnetic force radiating from the nucleus to the electron and returning from the electron to the nucleus as quantum loop gravity, an infinity symbol. Out to the electron, back to the nucleus, out to the electron, back to the nucleus. So half of the electromagnetic force radiates from the nucleus to the electron and drives it to spin, and half of the electromagnetic force returns from the electron to the nucleus as quantum gravity. So the energy that radiates from the nucleus to the electron and drives it to spin does so along the 6 axes of symmetry. Here in this cube octahedron model would be these lines here. The electromagnetic force that returns from the electron to the nucleus does so along the Cartesian XYZ dimensions, which is through the center of the square faces of the cube octahedron. So here is X and Y and Z for the location of quantum gravity. We believe that in addition to the Cartesian dimensions that scientists currently use, we must observe the atom with these 6 dimensions in order to locate the atomic particles. The atomic particles have properties of self-assembly, and this supports the existence of a higher power. This opens the door to quantum levitation. And as a practical application, the auto industry could be revolutionized by the use of a polyhedral motor with electromagnetic gyroscopes modeled after the geometry of the atom. This is another system by which the motor would not lose RPMs at a traffic stop, as the RPMs would be stored mechanically. This would allow for more power on less fuel. The spinning electromagnetic gyroscopes would generate electrons, and this would reduce the size of the batteries. This is a catalyst for shifting the momentum of global warming.
Well, Einstein was looking for we've got the gravity of the Earth, and then we know how to measure that, but it's very small proportionately compared to, say, like the mass of the Earth. And what he was looking for was gravity at an atomic level. Now, presently, the way we look at physics is that the gravity field is so small by the time you get to an atomic level that it's almost non-existent. However, as the radius gets closer and closer, all of a sudden this field shows up at a quantum level, which we actually call ligand bonding. It's bonding like an octahedron. There's 2 different kinds of bonding. There's electromagnetic bonding, and then there's ligand bonding, which shows up in the transition elements. Well, we're proposing that this ligand bonding on 4 axes of symmetry as an octahedron is really quantum gravity. That's kind of it's there, but we don't know what to call it yet because we're not supposed to know that yet. The periodic table that we're developing could be used by chemists, scientists, mathematicians, physicists, organic chemists. So what we did is we applied tetrahedrons and octahedrons and cube octahedrons and rhombic dodecahedrons and for the positions of the electrons in the atom. Hydrogen, helium is 1 and 2, and then lithium up to neon is 8. The first 4 are based on the tetrahedron, and the second group from nitrogen to neon is so that could be solved for the centroids of the octahedron or a double tetrahedron, which has got 8 vertices. The next shell layer, number 11 up to 18, sodium to argon, is another 8, which would be a cube octahedron shell, which would contain the octahedron in the middle. And that shows where the next 8 electrons are. Potassium up to zinc, there's 12 electrons. The next jump is going up to xenon. Xenon is 24 electrons above zinc, and the model for that is a truncated octahedron. Cobalt was bonding in 6 directions, for example, with ammonia. And it didn't follow the cube octahedron model, so I thought I was doing something incorrect. But then when I revisited the cube octahedron, I realized that there were six square openings in the middle of the cube octahedron. So this explained the location for the ligand bonding for cobalt. So that was a very interesting discovery. And also nickel seemed to have characteristics that were in between cobalt and copper as with a different kind of geometry, and this geometry was based on the rhombic dodecahedron, which was different than the cube octahedron. The rhombic dodecahedron and the cube octahedron are inverses of each other. The cube octahedron has 12 vertices and 14 faces, and the rhombic dodecahedron has 12 faces and 14 vertices. So they're kind of married to each other. We present a paradigm shift for the geometric order of the lanthanum series by placing it back in the numerical shell order within the periodic table. We present the series as a rhombic dodecahedron which has 14 vertices. This model is included in the Johnson solids and could also be related to the lanthanum series. So 32 is 32 and 54 makes 86, so that's the atomic structure of radon. And then to cap off the periodic table, 32 electrons would be the truncated rhombic dodecahedron, and it has 32 electrons in it. Well, the really interesting part of this crystallography theory is that the transition elements have a dynamic property that most rocks don't move, but the piezoelectric crystals, the superconductive crystals, the quasi crystals, and the nanocrystals with crystallography have properties of self-assembly and moving, and these are the elements that show up in all of our electronic devices and our speakers and microphones, such as barium titanate. But anyways, we made a model. The 1-1-1 triangular planes, the 8-1-1 triangular planes rotating on 4 axes of symmetry, and this explains the geometry where these crystals can rotate on 4 axes of symmetry and show icosahedral or pentagonal dodecahedral symmetry, which was considered not part of our current curriculum until Dan Sheckman discovered quasicrystals.
Since some viruses have fivefold symmetry, could the key to unlocking them be found within the dynamic property of quasicrystals? This is the HIV virus, which is shaped as an icosahedron, an extremely strong geometry, which could explain why it is so difficult to cure.
Another interesting facet of this geometry is done by the Berkeley scientists. They found in nanotechnology in platinum, gold, and silver that in solution they will form tetrahedrons and octahedrons and cube octahedrons and truncated octahedrons, which is the very geometry that we're trying to establish dimensions to. They also have the property of self-assembly, which could be explained by the quantum loop gravity theory, why they are bonding to each other when they fall at the bottom of their sample experiments. And those elements exhibit properties of catalysis.
This is a CAM model of present that Jim Sawyer from Sixth Dimension Design has made for the birthday present of Roald Hoffman, who is a Nobel laureate in chemistry, and I'll talk a bit about Roald later. But first about the chemical structure. So the chemical structure is a solid, and it has the formula of 1 barium atom, 2 iron atoms, and 9 aluminum atoms per indivisible smallest unit. And within this structure, the aluminum atoms make up these octahedra that share vertices with each other. And the iron atoms would be found in the triangular portions right here. And here in these hexagons is where the barium atom would go. And Jim has denoted that by the red triangle, and also put a polyhedron in there to symbolize the presence of the barium nucleus. So this structure right here, the triangular and the hexagonal lattice, is known as a Kagame net, and there are many Kagame nets, triangular, hexagonal type nets, present in nature that are well studied. So Rold and his PhD student, Gregory Vayenye, studied this compound theoretically using something called extended Huckel calculations, which is basically a way to approximately solve the Schrödinger equation that can tell you something about the bonding and the properties of solids and molecules. And they carried out these calculations and published their findings in a paper in the Journal of American Society in 1998. And what they found in particular is because these aluminum atoms, they share vertices with each other, this has an impact on the so-called electronic structure of the material. And what they found is that the best bonding between the aluminum atoms is maximized when you have a so-called magic electron count of 9 electrons per aluminum octahedral cluster. So that could rationalize the chemical formula of these systems and also the structures that they adopt.
Another very interesting property we found is that by applying the cube octahedron and the octahedron, the tetrahedron to the nucleus of the atom, we found that that Stephen Hawking's 12-quark model fits perfectly with the cube octahedron. Presently, Stephen Hawking's 12-quark model with up and down quarks represent protons and neutrons. Well, the 12-quark model could represent the carbon-12, where there would be a quark in the vertice of each one of the vertices of the cube octahedron, and it explains the geometry of the nucleus of the carbon atom. And we made a model of that. If you can see the model, cube octahedron quantum gravity, shows the location for the spinning quarks. What we found is that the 12 quarks that Linus Pauling speaks about, which represent neutrons and protons in up-down position, actually align perfectly with our cube octahedron model as a nucleus. Even Nigel Calder diagrammed that in his book.
Each sphere in these models represents a nucleon. Each color segment represents one dimension in the tetrahedron-octahedron truss. The truss is made up of square grids and triangular grids. The square grids for the models are shown on the left, and the triangular grids for the models are shown on the right. There are the same number of nucleons in the model as there are in the square grids on the left and the triangular grids on the right. We present a paradigm shift for the concept of atomic mass, whereby it is related to the number of nucleons. We are normalizing the standard model for quantum theory by orienting gravity within subatomic particles. We accept the nucleons as a combination of up-down quarks representing protons and neutrons. We hypothesize that the strong force could be generated by positive and negative charges within spinning quarks, which connect to the electrons through quantum loop gravity. The tetrahedral-octahedral packing of the nucleus accurately represents atomic mass for all isotopes. This explains why cerium-140 has a greater atomic mass than barium-140. We see that the quantity of triangular planes represents atomic mass. Our six-dimensional periodic table for the nucleus is a work in progress, and we continue to discover the geometry of more isotopes.
The water artifacts at the International Bureau of Standards are known to fluctuate in volume with environmental conditions. This affects the standardization of measure. We propose the use of the diamond crystal to replace the water liter artifact for the kilogram. The diamond's composition as a tetrahedron octahedron truss would not fluctuate in volume with environmental conditions, and this would improve upon the use of Avogadro's number. We are presenting that everything in nature is composed of the equilateral triangle and the tetrahedron octahedron truss. Everything is triangles, and triangles are everywhere. We have a hard time picturing this because everything man-made is composed of 90-degree angles. All the screens, the paper, the rooms that we're in, the windows that we look out of. We must think outside the box. We believe very strongly that the educational curriculum needs to include this triangular geometry at all levels of development. This will open our minds to understanding this new spatial reality. We are suggesting that everyone figuratively put on a pair of glasses where the lenses have triangular grids and take another look at whatever you're working on. Ask yourself, how does the equilateral triangle or the tetrahedron octahedron truss apply to my work? For example, the air traffic control could become dramatically simplified if a triangle map of the Earth were used. This would eliminate the need for conversions between stations, which is a known problem. If photovoltaic cells in solar panels were arranged in a triangular hexagonal grid, there would be more energy generated by less surface area. Computer graphics could become dramatically more lifelike if triangular pixels were used and if computers were able to process with triangular dimensions. And think of the implications a better understanding of chemistry would bring to the healthcare industry as far as medical treatments and pharmaceuticals are concerned. The collection of everyone taking this back to their desk is the revolution. We can do this.